Hello everyone, my name is Maz Barami from Wolfram Research. Welcome to the 8th session of the Simplified Machine Learning Workflows with Anton Antonov. If you join us for the first time, Dr. Antonov is an applied mathematician with more than 20 years of experience in algorithm development, natural language processing, and machine learning. Today will be the part 3 of the Latent Semantic Analysis Workflow. Handing over to you, Anton. Looking forward to your 8th session.
Thank you, Matt. Thank you for the introduction. So in this session, the core part of the session is the linear vector space representation. But before jumping into that, or instead of just jumping into that, I would like to review the last session's example we considered, which was finding the most important questions given to me in some course I taught a year or two ago. Also, I'd like to review a motivational example, which is demonstrating a full-blown latent semantic analysis workflow. The linear vector space representation is a fundamental operation, and there are several, first of all, several important assumptions and several important operations which are done on the data. In this particular package I'm using, the central object is a matrix with named rows and columns, and I'm going to explain how exactly this is being used and how come I'm using it and so forth. I would like to bring the Pareto Principle adherence again, and we're going to see it being applied to a single document and to a document collection. Also in general, the Pareto Principle is just general, but it does apply to terms in the documents and to the distribution of both documents and terms in a given collection. This is important in order to make decisions how we actually extract the topics, how we extract the thesaurus, and so forth. This section here, it's the same as in the previous session. This is an overview of the document collections I'm using in this cycle of sessions for latent semantic analysis. I might add one or two more, but right now we're going to be looking into this Raku documentation and the data science class questions. So I'm going to start with the data science class questions. It was a class which I taught parts of it. I was like a teaching assistant or guest lecturer to big data in healthcare class. And when I finished my guest lectures, I was given around 100 questions. And obviously I couldn't answer these questions in, say, 45 minutes. So, and instead of taking random samples, like what I'm doing right now of these questions, these are 100 questions, I decided to use latent semantic analysis to find out which are the most important questions. So one way to do that, to find the most important questions in an automatic way, is to use latent semantic analysis. Here you can see these are the questions which were being extracted. This can be visualized, the process, the application and the process of finding the most important questions. So this is a bipartite graph, which shows the connections between the questions. The questions are red nodes are the questions. The blue nodes are the words. So the most important questions, they have the most important words, and the most important words are in the most important questions. This is somewhat cyclical kind of definition, but this basically, it can be used to produce reasonable results. This graph is a bipartite, which means that the red nodes do not connect to each other. Red nodes connect only to blue nodes, and blue nodes connect only to red nodes. We don't see connections between blue nodes and red nodes and red nodes. We're simulating millions of random walks on this graph, and the nodes which have the most frequently visited by these random walks are the most important questions or words. And so this is how this is found here. The procedure I just outlined is how PageRank works. The Google's algorithm search engine PageRank, which was introduced a few decades ago. All right, so this was the last session's example. The full-blown motivational example is which I presented last time, was on the documentation of the programming language Raku. Raku initially was named Perl 6. Raku Perl 6 is a valid name. Just Raku now, it's also valid name. Perl 6 is it's different language from Perl 5. It's a different language. Very similar. I mean, quite a lot of similarities. Very different language also. So the example here was to take the documentation from GitHub of the Raku language and apply the typical latent semantic analysis workflow over it, and basically get some sort of summary or review of what is being discussed. And so I'm not going to go further into this, but what I'm going to show is that this here is this generates code instead of using the natural language commands. I could have used this code, which is similar to what we, like follows the same type of workflow, which was presented earlier for the big data in healthcare questions. So I could have evaluated just this. It's going to produce exactly the same results. Instead, I'm using the natural language commands because it's easier for me to describe what is going on. And so I'm going to actually go through these commands here. We take a document collection. We make a document term matrix. This is the linear vector space representation I'm talking about. This is the most fundamental operation. Then we display certain summaries like what you see here. And then we apply certain latent semantic indexing functions based on the statistics we have observed. We extract topics using certain methods, steps, whatever. And then we actually can show the topics and compute statistical tesoros for selection of words. So this is what we see here. So this was the full-blown latent semantic analysis workflow. The vector space representation. So actually here, before going into that, I would like to mention that since we are discussing last session, in the Wolfram function repository, this function non-negative matrix factorization was approved more or less at the time when I was making the presentation, my last presentation. The example which was discussed, the workflow which was discussed, there were two examples. One was the hard way, doing topic extraction the hard way and doing it in the easy way. The hard way is fully spelled out here. This is from the last session. You can find it here. There is also, and you can see how this was on the movie reviews. You can see here the different topics. You can also see the corresponding thesauruses. Also, yeah, the comparison between the methods, this is something I mentioned last time, is also in this function page. All right, so this actually, this relates to the independent component analysis function. So independent component analysis is also used in this software more that I'm discussing. If I put here, say, ICA, the code, I should put it here, the code which is the generation, the code generated and the computations we're going to be using independent component analysis. This independent component analysis is corresponds to this function here in the Wolfram function repository. All right, so now, since I've been talking about the most important function, and most fundamental operation in latent semantic analysis. Let's start actually discussing it. So I can take, I kind of trying to decide which data to use, but let's say I'm going to use the big data questions, right? So I'm going to do, so we see here a sample of questions. I'm going to, in order to make the explanations shorter and easier and the graphics easier, I'm going to use a particular sample of these questions. And so what I'm going to be doing here, it's, I'm going to make a, I want to see the matrix representation. And so here I'm going to just specify this, this workflow, simple workflow. I'm taking this questions, this texts, sorry, the text parts of the questions here. They're going to be part of the monad, and I'm making the document term matrix. And when I make the document term matrix, I can choose, should I do stemming? And in this particular case, in general, with small collections of documents, it's a good idea to do stemming. And should I do stop words? So I have my object. I'm going to extract the the actual matrix from it. And yeah, you can see. And let's actually see what is this. So first of all, let me show a matrix form. So this 20 questions or 20 documents. So when I say, when I work with this monad, latent semantic analysis, the items we're discussing, they're documents. In this particular questions, in this particular situation, example, our documents, each document, it's actually just a question. But, and I might say either a question or document, but in general, the objects we are dealing with, documents, and the objects we are, which are representing these documents are called terms. The reason they're called terms, not words, is that if I actually do here a stemming, and so this needs to apply the word data porter stem. I mean, if I do this, now the words here, they're going to be, they're not exactly words. They're basically stems of the words. That's why I would say document term matrix. So what we see here, each document is being represented in the space of the words. I have 120 unique words after the stemming. If I didn't do the stemming, which I'm going to return to no stemming, I have slightly more words, just one more. But now we actually see that each document is a point in this 121 dimensional space. And so what is I can also go further and do a matrix plot, which is further can summarize this matrix. So this is a representation of the data you see here in the matrix form, right? And so if a term is, if a certain entry in this matrix is 0, it's not going to be displayed. It's white space here. But if you have 1, which is here around row 9 and column 1, yeah, we have something. So this document, this matrix, this document term matrix is actually something more complicated. If I show, let me see, can I show this? Hopefully this is not going to be too bulky. So this actually has, this object has a head S sparse matrix. And here we have it's inside that we have a association, we have a sparse array, and we have row names and column names. What you see here in this is the row names. What you see on top here are the column names. the object knows certain things can be done with it. Like say, for example, I can find the sum of the rows. So if I find the sum of the rows, this is going to tell me each document how many terms it has, right? I mean, obviously, right now I have one. I don't think I have any. No, I have some documents. Some terms appear twice in a certain document. But yeah, so actually when I sum the rows, do the row sums, I can find how many terms each of these documents have. And you can see that say there's a particular document which it has 18 words, and some of them have 12, some of them have 7 and so forth, right? So the sparse array which corresponds to this sparse matrix object, and I'm going to explain the name, is it can be retrieved with sparse array. I can do something like this, and this now is just a simple, but it is just the typical sparse array object Mathematica has, built-in object. The one here with the S sparse matrix, it's more. It's basically a sparse array together with the row names and the column names. Now, this is why S sparse matrix. There's a language called S, the success, which was used for statistics. Made a long time ago. Like probably very similar time frame. Wolfram Language was made, Mathematica. The successor of S is called R, and that's why we have the name R, because R the letter is after S. So almost any both S and R make a lot of sense if you have taken statistical classes for 1 or 2 semesters in the university. And so almost all objects there, any kind of table, data frame, matrix, list, has the elements have names. The data frames, they can have named rows and columns. The matrices can have named rows and columns. This is very useful. Imagine you actually have a full-blown matrix arithmetic in which whatever you do, the names and of the rows and the columns are preserved. You actually can do quite a lot of interesting stuff with it. For example, here, if instead of I do column sums instead of row sums, I can actually see which words are the most popular, right? So I can do, say, reverse sort. And I can see that, say, data is the most popular word, learning is less, and so forth, right? Not a big surprise, given that these are questions for big data and healthcare type of class. So let's actually go further with this, and I'm going to show the arithmetic here. So if I multiply, I mean, obviously, if you have this matrix, I can multiply it by 10, and I don't expect the pattern here to be particularly different, but yeah, well, it is it is supposed to be the same. But when I do the actual printout of the matrix, you can see that the actual entries, they have been multiplied by 10, and say, words like, say, data, which are very popular, right? I mean, you can see that we have some other entries like, say, 20, because initially there was term 2 and so forth. Similarly, we can do, this is just a Scala with the matrix. Similarly, we can just add. Now you can see the addition here. So when we put 10 plus this, obviously the background element needs to be treated. This kind of objects, surely we should be able to transpose it. Why is this important? Well, we can actually compute the similarity matrix between these 20 questions. This actually tells me how similar the two the questions here are, and you can see I have, say, obviously, like say question 5 is going to be more similar to itself, right? Or document 5 with this ID is going to be more similar to itself. But I can also see what is the similarity with the rest of the documents. Obviously, this similarity matrix, let me see, can I do this here? Maybe it's going to be detrimental. I mean, I can do it the other way around. I can actually multiply the transpose of this matrix with the original matrix, and this is going to tell me what is the similarity between the words, between the terms in this document term matrix. So if I do here matrix form, I mean, at least in principle, I should be able to see what is the similarity, say, with the word. I can see what the word curve shares with the word advice, at least 2 questions, similarly with all together, and so forth. So this is way too big. So I'm going to, the message here you see is that it is a good idea, the different dimensions of the matrix to also have names. This is not an error, this is just a warning, but when we do this multiplication with the transposing, the dimension names are equal, and so there's some renaming. All right, so I'm going to actually comment out this because it's a little bit the output is too big. And so for the application of this, if I take, let me show here, if I take, say, without normal, let me just do normal, right? And let me do then sparse array. So if I take the sparse array, and this is going to tell me this here, it's basically taking the 5th row of this sparse matrix. So I want to multiply the 5th row, very similar to what I'm showing here, right, with the transpose. I want to multiply the 5th row with everything else, and I want to see what is going to happen. This is going to tell me what, obviously, the result is going to tell me how many times this document with this ID 005, how many words it has in common with the rest of the documents. And you can see what, say, with 0016, it has 2 words in common, 017, 2 words in common, and so forth, right? Obviously, it has most, it should be most similar to itself, right? And I can actually, I mean, this can be done. I mean, again, I can do this I mean, I can extract this as association. One way to do that is to apply this, whatever I'm doing here, and see which are the most popular documents. So what is this? And I named it fairly, explicitly here. We can actually use this matrix arithmetic to find most similar documents. If we assume that the documents which are similar, the similarity is measured with the cosine distance, or cosine similarity, actually, to be more precise, with the cosine similarity. Meaning, if certain documents have relative distributions of their words which are similar, they're going to be vectors which point in the same direction, and we can find this. We can find this with matrix arithmetic. This is a very fast operation. It can be used both in latent semantic analysis, can also be used in say, recommendation systems, which there's a strong relationship between what I'm showing here and recommendation systems based on the information retrieval paradigm to which latent semantic analysis belongs to. So let's actually see some examples here of these are the actual kind of most similar, like 13. What was 13? We have only 1 word in common with 0.5. Well, I cannot see. I guess this is the word right, or whatever. And so anyway, this is one of the things. This matrix, sparse matrix object with named rows and columns. The full name is somewhat clunky. That's why I have taken the name as sparse matrix. It is a fundamental object, as I mentioned, in languages like, say, S and R. It's extremely convenient to do the computations with it. And I have done it to a point. I have, like, say, for example, I have overloaded most of the most frequent functions for this. If I want to do something like this, this should work, say, right away. And the matrix here, which is going to be shown now, all elements here, they should be just ones. Like, say, the most popular word, which was data, right? I mean, you can see now it has only ones. There is no entries which have larger than one, because I made this clip. So, all right, this was what I wanted to say about this object. And let me do here. So back to this steps. Like this is the overview, of the session, the actual subsections I wanted to discuss. So in latent semantic analysis, the fundamental assumption, scientifically speaking, is that words with similar semantic meaning, they have similar distribution in the space, in a purely geometrical physical space, like, say, the document itself. And this distribution can be measured in two ways. One is that words with similar semantic meaning, they might have similar neighbors, and they might appear together physically in the text. Or if one of these words is there, if the other one is not there. This is similarity by absentia, and then this is the so-called paradigmatic similarity. And for this, we're using the thesauruses, which I was showing here. That's why, for example, I'm showing the thesaurus. So this fundamental assumption allows us gives us the right to do the linear vector space representation, in which we ignore the order of the words. We make this representation the bag of words operation, in which we basically, as I said, ignore the sequential order of the words. We just count how many times the words appear in the documents. And we actually can represent each document. We can see, but we can represent it as a matrix. We have quite a lot of both linear algebra in general and sparse linear algebra algorithms already developed, and they can be utilized in order to extract topics, do some other stuff based on these distributional assumptions. This non-negative matrix factorization, independent component analysis, this is when they are applied. They're basically matrix factorizations. All right, so another thing to see here is about, so this is another function actually from the, I'm not sure did I discuss this, but this is a function from Wolfram function repository, well, again, submitted by me. I'm a big fan of the Pareto Principle. The Pareto Principle can be seen to apply in different situations. In this particular case, you see it applied to lake data. Let's actually see how this applies to the documents we have discussed. And I'm going to just look at, say, this is this text here. It's just the text Hamlet we have from Mathematica Hess, and it's an example data. I have separated the words, the words from this text. You can see we have like 32,000 words, and then I'm applying so looking at the tally, right? I mean, after I have done the words, I can actually make the tally of the words. I can see what some words, like, say, king, appear very often. Off is a stop word, so it appears also very often. The is a stop word, and so forth. And so the Pareto Principle adherence shows it's a particular statistic which tells me that looking at the tally of the words, around 15% of the words correspond to 80% of all words. So if I remove, like randomly remove 20% of, sorry, if I randomly pick, yeah, actually, let's go with remove. If I randomly remove 20% of the words, a big part of the words which stay might actually be in this top 20%. Alternatively, I can actually keep only the words, this 15%, top 15% words, remove everything else, and this I'm going to have a text which is very close to the original one. Doesn't necessarily going to be at the same meaning. So this is the reason we're using inverse document frequency, because we don't want words which are way too popular and not that good for finding semantics. It is very interesting to see how this tally is going to be done to look like if we remove. And let's just, in order to do that, let me do here some image. Specify the image size in order to be able to compare it, right? And so, I mean, we can see what the second one, actually, we can do something better. We can put them together. So the first one is without the stop words being deleted. The second one with the stop words being deleted. The orange line is the second one. You can see probably the tooltip, it says 2, and this here says 1. So after deleting the stop words, the Pareto principle is not that pronounced, and this is to be expected. It's still fairly pronounced nevertheless. 35% of the words correspond to the 80% of all non-stop words. So 35% of the non-stop words correspond to 80% of the non-stop words. Still, you know, we have a strong Pareto adherence. This is related to the so-called Zipf's law, and I discussed that this is one of the justifications to use inverse document frequency. This can be evaluated systematically over the collections we are dealing with. You can see that when I'm doing the statistics, actually, I can I can actually do the Pareto statistics also, which by default I don't. I had to specify the functions. If I take the documents from the Raku documentation, I mean, we start to see this typical Pareto principle adherence. With this, I mean, these plots here, they tell me what is the actual distribution of the terms and the total number of occurrences, the terms distribution across the documents, and the documents, Pareto principle of the documents, knowing how many terms are in the documents. So I can see here, for example, that 30% of the documents have 80% of all words in all terms, in this documentation. Similarly here, I can see that 30% of the terms, they're basically represented in
Anton, quick question. When you talk about document for a text like Hamlet, so what's going to be a document in Hamlet?
In Hamlet, this here, what I was showing, there is no document per se. I'm just counting the words. So this was a single document adherence. So I'm just counting the words. But I can actually do I don't know. Well, I can do sentences maybe. I mean, ideally, I should do not sentences, but I should do the split between you see, when I make the split here and I use full stop, semicolon, question mark, and so forth, right? And if I remove this, so I strongly suspect that I'm going to have sentences. Now, each of these sentences is going to be a document. I can make this. I can make the documentation, the latent semantic analysis workflow, I can do it on these sentences. So echo document matrix statistics, and I can do, say, LSM on. These are very, Hamlet is a very relatively small text. So doing the, doing the topic extraction and etc. might not be that produce that interesting results. But so here I'm going to do 12 steps, and yeah, I'm going to finish here LSM on echo topics table. Let's see what is going to happen. And so, yeah, we can see here, well, actually, in order to do this, I'm going to do a number of table columns to be 6. And here I'm going to do, since we're discussing this for Pareto Principle, so, right, we can see the representation of the terms and the documents, across each other, and we can see here, the topics which have been extracted using this using the latent semantic analysis. Again, each document here is a sentence. If I show you a random sample of this, they should make sense like sentences, right? So, I mean, obviously not necessarily great, and yes, this is just a way to kind of split this text. Would have been better if the documents, if we have made the separation by the different parts. When a particular character speaks, this would have been a better separation, not the sentences, but the actual speaking part of the characters. That's actually a much harder kind of thing to do, given how this text is represented. And so that's why, I'm not doing it. Like, say, this is the part of Horatio, right? And I need to find here where the part of Horatio finishes. I mean, say somewhere here or whatever. No, actually finishes here, but then this is better, and so forth, right? This is not necessarily trivial parsing exercise. I mean, it's not something I can do very quickly, so I split it in sentences using typical sentence punctuation, and then then basically making the latent semantic analysis. So let me so similar thing to do is to actually look into human rights documents, and I'm going to show this here. So if I do, let's do English first. So we have a bunch of human rights documents, and so, I mean, let's say I have Russian, right, and so forth. So what is, again, this is a single document perspective. And if I make this plot, and here I'm going to make the plot larger. So, I mean, we see that the Pareto Principle is there, right? I mean, but we actually see quite a lot of, I mean, several outliers at least. Japanese is an outlier, Maori, Hawaiian, also Russian, Latin, and Korean, obvious outliers. English is somewhere here, right? I mean, some of this, wherever it is, right? And why, for example, we have these languages being separated from the rest, and these languages here, they kind of have the same type of distribution, more or less. Well, the one of the fundamental assumptions in going back to this, one of the fundamental assumptions here for the linear vector space representation, in order to apply it, and for latent semantic analysis, is that the language we deal with, the words are easily separated, or the texts they're separated in the text. And what I'm going to show here, it's how with the human rights document for Japanese, actually that doesn't hold. Okay, so I mean, we can see that using just spaces or punctuation signs, these are complete sentences. These are not words. Because of this, we have way too few words. If I split this as with spaces, right? And I'll have the number of words. Okay, come on. The number of words is going to be way too small. Not like, say, something which is like, if I take, say, English, presumably English is our, things we know. And so it's like, yeah, 10 times less words, because these are not words. That's why we have this outlier. If we look into what is say, Maori, right? We have quite a lot of small words which are being repeated. And so I'm going to demonstrate this. Yeah, so we can see, yeah, we have much more words, but there also quite a lot of them are repeated in certain way. So we have, that's why we have a much more pronounced Pareto distribution here. Now, Latin and Russian, they have similar structure, in a sense. They use cases, and very often in Russian, the same word can have being in different location in a sentence, a different part of speech. It actually can take different inflections. And so because of this, although the core number of words is probably the roots of the words, probably the same as saying in English, kind of roughly, because of the different grammatical suffixes, grammatical rules applied to those words, which produce different suffixes, we actually start to have much more different words. Latin has some similar kind of grammatical structure. And because of this, that's why we have, since we have more words, they actually appear in this way. We have less pronounced Pareto principle. All these are important considerations to take into account when we are dealing with texts for natural language texts, and we apply latent semantic analysis. Of course, latent semantic analysis can be applied to data which is not necessarily with language related, and some of the typical applications, in some of the typical examples with Pareto principle, they can actually serve as a proof. I mean, Pareto principle applies to not just words, to other kind of data, both categorical and numerical. And this actually is going to justify the application of the functions like what we see here, like say, functions like IDF and term frequency and cosine. So this is what I had for the session today. And any questions?
Thanks, Anton. Let's see. There is no question on our Twitch channel, so I think we can wrap up our session. Thank you, Anton. You were watching the 8th session of the Simplified Machine Learning Workflows with Dr. Anton Antonov. You can find the recorded videos on the Wolfram YouTube channel. You can also interact directly with Anton through the Wolfram community. Thanks for watching and have a good one.